continuation of lecture 2A, and then we'll do number 5 after this. And then I'm going to have you guys work on assignment number 5. So you'll have some time, don't worry. I'm not going to lecture to you all day, most of the day today, but not all day. Let's see, so, because tomorrow I'm going to give you more time to work on stuff, like the CSLO essay and stuff like that. I stopped a little bit after this point, but I wanted to start here because it's a good starting point, talking about context switching. And this is definitely in reference to CPU scheduling and how we switch between processes when we're running it on the schedulers running those processes. And the context is nothing more than the reference to the working kernel memory. What context? It's at one point working on something. So context could be for the running process that's running. It could also be for servicing an interrupt call or for doing something else. It's basically the context for which the kernel is working. The user mode context is you've got a Word file open and you're editing it, or an Excel file or something. We don't necessarily have the same kind of concept. It's kind of very unique to the concept of the kernel. Now, when the kernel loads something into memory, it's usually called a loader. We have a linker and a loader process. Most modern-day operating systems, the kernel is responsible for linking and loading. And then we've all heard of dynamically linked libraries and shared objects and things where we delay some of the loading until runtime. And then we have the kernel load up and the running program, the executable program is running, and then do the dynamic linking to any shared code or any shared library that's out there. So the loading and executable, as an example, user compiles the program. It's an executable file. It has a set of headers, as I mentioned before. In C, C++, Java, we have binary code, machine code. It doesn't have to be for all operating systems. In Unix, it could be text files. It's the header of the machine, of the file, and then the writes. So if you don't change the mod to make it executable, it's not executable either. Going back to the inode thing, if everything has a place in the inode and the inode's permissions isn't set correctly, there's no way that thing's going to run, even if it is an executable file. So it has to be set to be executable by the user or the group. So we usually have some sort of machine language representation. It doesn't have to be binary or machine code. And we have the other sections of the process space holding the symbol table and some of the other things that are in there. And I discussed briefly last time the loading of the executable into the 3 spaces, and we kind of looked at that from a text data stack perspective. We're really primarily interested in that stack. So it's automatically creating a size of the entries dynamically by given the number of instructions. So one of the ways that we make executable files more efficient is reduce the number of stack entries. So there's a lot of compiler switches, especially with the old C compilers, that made a smaller footprint, made a smaller file, fewer stack entries, runs faster. We also have options that we can compile for better optimization for memory usage, less memory usage, more memory usage, less stack entry. So we can kind of customize. In the old days, we used to customize how we built the executable files instead of just randomly just building a blank file like what we do today. So usually today, most people just type in GCC and an output name, and then they get what they get. And they go, oh, I'm happy with it. But if we have unlimited memory and unlimited disk space, we don't really care about it. We don't care because the processes are pretty fast. How are we going to notice if it's got 10 more entries in the stack than needed? We're not going to notice that either. So, but if you're working with an embedded system or with a system that has more limited resources, then you start playing around with the switches. So here we have the 3 parts, or they're also called regions. The text corresponding to the text sections of the executable file. The data, and you're wondering, what's the text? It's kind of interesting, the concept of this text. It's actually the text. So when you have something like, for example, hello world being printed to the screen, you compile it into an executable file, bring it up into a text editor, you'll see hello world. Text never gets converted. So the text is actually part of the raw data that's being used in that executable file, which is the most ironic thing. You think the whole thing would be converted over. So a lot of people take, and there's a market for this, actually you can download it. It's called a hex decimal, or actually no, mostly it's a hex. You just Google hex editor, hex code editor or something like that. You can bring up an executable file and you can change all the GUI as an example. How do you do that? Some of them actually parse it out for you, and they show you all the text together. And some of them like have it so it's mixed in with the machine code, or it's not readable. Some of it's not readable, and some of it is. And then you go in there and you start changing the text. So it says, oh yeah, this program's by Barbara Hecker instead of Microsoft or something. And the name of the program. Problem with that is that if you're off by a byte or something, you change the wrong thing, it's going to mess up. So people do that with, well, viruses do this all the time. They'll just change something in there so it says their name on it instead of something else, or it's a long time hex editor. It's kind of like the poor man's virus creator. It's definitely a low-tech kind of way of messing up somebody's command.com or something else. By having it said Microsoft, it says spiderware or something. I don't know. It says something different, but just changing the text. But long story short, the text is also corresponding. This is the text I'm talking about. It's corresponding to the text of the executable file. All that text in there gets loaded in a separate section. Why do we got to deal with it differently? Because it's kind of a special kind of concept. It doesn't translate very well. It's hard to translate it back, so we just leave it in text. Plus, this text doesn't take up that much room. The data corresponds to the data section. Well, that's going to be all the other things that's not text. It's all the data. And also on the stack, when the stack entry makes a piece of static data, generally goes in the static area. So integer I is going to be down there in the data section. And then the stack, automatically generated, suggested by the kernel at runtime, because the kernel is going to add entries and remove entries from the stack when it's running its program. So the compiler generates an address for a virtual address space with a given address range. That's the interesting thing. So Unix actually uses a set range. Again, there's been, just like with the mapping between threads and processes, there's been experimentation all the way down from the beginning of Unix with, should all processes be given the same amount of disk space, or memory, I should say. It's memory that they're getting. It's kind of a controversial question. Is it one size fits all? Do all processes require the same amount of memory? Well, the problem was originally, you go through, you look at this, and you go, oh, how this one only needs this amount of memory, and that one only needs that amount of memory. Talk about your internal and your external fragmentation. If you have all these different size processes, then you got to go worry about fragmentation. Is the hole big enough to hold this new process? The hole in the memory that you're going to pick. And if you're not using a paging scheme, because some operating systems actually don't use paging. You don't have to. There's no law that says you have to create pages. So long story short, it was way too complex. So everybody went one size fits all. And how do you know one size really fits all? Interesting question. If you're running a runaway memory leaking C++ program, one size doesn't fit all. One size crashes. Because you need more memory because you're not using the memory wisely. So now you're making waste while the program's running. Well, the funny thing is, so does the operating system. So in the beginning days, Windows used to crash all the time. Blue screen of death, all these little memory problems. Because some of the processes actually outwrote their process space. And you say, oh, make it bigger, make it bigger, make it bigger. So then as you change the runtime environment, you go from a 32 to a 64 runtime, you go to a larger process space, kind of different configuration. Problem with that is then you get internal fragmentation. So you got rid of the external, now you get internal. You got all this process space for hello world. Same amount of process space as my Oracle database is taking up, or something similar to it. A couple of my processes there. Not fair, really. So that's still the age-old problem. It's program by program. It doesn't really matter how big the program is. It's going to take up about the same amount of process space these days. So the memory management unit translates the virtual addresses, generates by the compiler into physical. Physical addresses are allocated in terms of virtual memory, in terms of that mapping. I'm not really going to cover memory management in this course. It doesn't really apply to Unix. It's more of an operating systems concept. But memory management is actually very interesting when it comes to operating system design. So the boot and the init process. So if everything on the system is a file, everything on the system is also a process, even the kernel is a process. So everything's a file and everything's a process. So all right, so that's pretty clear. So we boot up the system, And then we have to worry about the numbering scheme. So kernel doesn't get a number, because kernel never goes away. What do we need a number for? The brains of the operation. Administrator initializes the system through this bootstrap sequence. So when we went back and looked at the disk image a few slides ago before lunch, we say, oh, there's this like bootstrap area, then we have a boot sector area, and we have the system inodes area. We have all these little partitions at the front of that disk. You know, we still have a boot disk, but we can load in what's called a bootloader, and then switch between different disks if we want. But we've got to put the bootloader somewhere. Usually they put the bootloader on the disk. So Grub or Lilo or one of the other. Grub is pretty popular. Lilo's not so popular anymore. Or maybe it is. I don't know. Most people are familiar with Grub, actually. What is that? It's a bootloader. The bootloader comes up first. So you still need a disk in there. So you put one disk in there, one hard disk. Maybe on the hard disk there's 5 different operating systems or 5 different kernels. You decide which kernel you want. The kernel is really the operating system. So you could put different kernel builds on there, have a little menu, grabs the menu system, comes up first and you pick, I want this one, I want that one. Battery, you could dual boot your Windows machine, put Linux on it, and then select Windows as one of your options. That works well. Or Mac, you could do it with a MacBook. Select Mac as one of your options, and then Linux for the other one. Don't know why you would do it on a MacBook, because you already got BSD Linux on it, so you're dual booting into it, essentially. But long story short, bootloader and boot system, or boot sector, different concepts, but they all work together. Bootloader comes up, and then it picks the boot sector of whatever disk or whatever starting location, and whatever kernel you want. So we have this thing called a bootstrap sequence. So bootstrap is the kernel loading, and then the kernel loading everything else on top of it, after it. So the kernel is like command.com in Windows, and it goes in. The old days it used to work with an autoexec autoexec.bat and config.sys. They used to take this config.sys for the drivers and for the devices. This is DOS, this is not Windows. You used to go back, have these 2 support files that went along with command.com. We still have command.com in Windows systems. We still have these 2 files too, but they're optional. I think, don't quote me on this, but I think maybe the files have gone away with Windows 8, but I'm not sure. Long story short, we go back to XP. XP still had these 2. That's equivalent to init. Init and some of the other processes. So not everything's going to be in command.com. Well, command.com is the kernel. So you load up command.com or the kernel. Boot sequence eventually reads the boot disk 0 of the disk and then loads that into memory and then loads these other files. These other files like init. It's a process that's created. It's really a program that's running, an initializer running, where you can just list a bunch of stuff to be loaded, resources. So mount this disk, use that disk, set up this up, maybe make 5 terminals, maybe do this, maybe do that, remote logins, all this other stuff that you want to auto load at boot sequence. So we have a boot block that loads the kernel from the file system, for example, /Unix, which is very popular. And after kernel loads, the boot program transfers control to the starting address of the kernel. And then the kernel starts loading everything. So it's like a dominoes. One thing leads to another, and we start loading everything. Where are we going to load it from? The file system. Where are we going to get the file system from? From the mount. So the kernel is going to mount the first disk and then load everything from there. So after initialization, kernel mounts the root file system and then handcrafts the environment for process 0. Process 0 forks from within the kernel. That's 0 starting point. And then we get 1, which is init, if I remember this right. Process 1 running on the kernel mode, creates the user level context. And then when you get into the user space, your shell gets a process number. And then everything from your shell is, again, treed out through more processes that you're creating when you run programs. None of the numbers are ever repeated. And it's interesting how the lower level numbers, in the old days there's a chart coming up in a few minutes here that will give you the accurate, which one's in it, which one's the boot. But long story short, somebody configured this initially to make it logical in terms of the boot order. And so the process order determines what gets loaded in what order. By the time you see it, your numbering system's up to about 5,000 or so, or I don't know. We saw it around 2,000 or something. I can't remember what we saw it at. So process 1 copies the code from the kernel space to the new region, forms the user context of process 1, and then we have process 1 setting up and saving users and registers, and the context returns to the kernel mode. So process 1 is now the user level. So the user level gets created and initialized. So we have another call that consists of an exec init program. So the kernel loads up the user space on top of itself. And then from the user space, we load up all of the other processes that work in the sequence. So let's see. I thought the chart was in here. It's probably going to be in the next one, actually. So this was 2A. I have 5 in my notes. I'm going to go to 5. I'm missing. Let me just check here real quick, actually. Let me pause this for a second. Okay, so lecture 5 is the right lecture, and there's a little bit of repeat on some of the stuff in the beginning of this lecture, and then towards the end we go back into the boot process. We pick up where the other lecture left off. It's out of sequence a little bit, but the information's in it. We actually went over 2B, 3, and 4 last weekend, so I'm kind of doing them out of order, so there's a little bit of out of syncishness here. But what is this one? We're going to review the file manipulation utilities. No, we're not really going to do that. I'm going to skip over that. And then we have the Unix process subsystem. I'm going to see if there's anything new in here. I don't think there is, actually. But we're really going to go over to the Unix shell and look at the different types of shells. Because what we're going to do next after this is write shell scripts. So that'll be probably, it depends on how much time I give you to work on stuff this afternoon. It may also be tomorrow morning. We'll see what happens. We also have networking to cover tomorrow as well. Okay, so file attributes. We already know about the change mod, but I wanted to give you the inode stuff. So it's actually stored in the inodes. So when we run the change mod command, we're changing our inodes. We're reading back and forth to the inodes. It changes permanently. Well, I mean, permanently means it's persistent. Automatically updates it. Turn the computer off, turn it back on, it's already changed. It's not going to go back. So we have the file owners, and we have the file permission. We have file modification times that are given to us by the system time. And then we have the type of file that we're looking at that's also changeable. So we can change a directory into a file, well, from a regular to a directory, or a link to a symbolic link to a special file. We don't want to, because then we're going to confuse the system and we're going to know what we're working with, but we could essentially. We know about the change mod. I showed that to you. We know about, or do we know about the change owner? Probably not. I haven't shown that to you yet. So you know we have different user accounts. They log into the system. Student 15, student 20, whatever. You're not, although you can see the directory, you're not the owner. The owner is set to another student. So you can actually see everybody else's stuff, probably. I don't know if you can or not. You probably can. And if you can, you can't touch it because your owner is not set correctly. So the change mod is per owner. If the owner of the file, the person who created the file, makes it public, that's great. You might make it public for the outside, for the group, but also for public, you might be able to see it. In that case, you should be able to see it. But if it's private to the owner, you're not going to see it. So how do you get around this problem? You change the owner. So if I have a file in my folder and I want student, I don't know, XYZ, I could change it to add student XYZ to the owner, or change the owner of the file. So files have ownership. They don't have this in Windows. There's no such thing as file ownership in Windows. A file is a file. There's no ownership. There's no security. But in Unix, we have an owner. We have a group association, and then we have a public view. So we have the 3 sections: user, group, and other. So the change mod is what we looked at in the first weekend. That's changing the permissions. You can change the file owner. We're not going to do that in this class, but you'll have some exercises in exercise number 5 that's going to work with some of this stuff. So I don't know if you're going to have to change the file owner. I can't remember, but I don't know. Don't quote me on that. They also have the change file group. So you can create a group and then put all the files into that group that you want. And then everyone who's a member of the group would have the 3 levels of access: the read, write, the execute, depending upon what was turned on. So 0, 0, 0 would be nothing, a 1, 1, 1 would be everything. The read, write, and execute by the group. So the group overwrites the owner. Other overwrites group. So the farther you go to the right, the more liberal you are, or the less conservative you are. The farther you go to the left, and only the user, the more protective you are. So as you move to the right, you're just going to open everything up to the world, essentially. Because group's next, and then others pass that. So it's a left to right kind of thing. Only the owner or the super user can change file attributes. You can't go into another student's directory and change the owner to yours. Oh, I didn't do the assignment. I didn't write the script. I want to get somebody else's. It doesn't work that way. So upon creation, the default permissions are given, and the file modified by a process called a umask value. You can actually list out the umask. You get it with ls actually, but you can list out the umask. So now we got the 3 types of permissions, and this is the review part. We went over this last time: the rewrite and the execute. We looked at the numbering system as well, and 777 and 750 and all the different combinations. And we set all 3 of the permissions for the owner of the group and the other. So we access checks made against the process's effective IDs. Like effective IDs, well, that's what the kernel calls them. The effective IDs are the ones that are located in the inode list, because all the stuff is in the inodes. So the inodes is going to store all this stuff. We're going to look at the effective IDs, and the root can change all of the effective IDs. So here's our symbolic accesses we saw before. We could use the octal access modes, or the symbol with the R to the W, plus R plus W, and the file name. We may or may not have set permissions on directories. So usually what ends up happening, especially if you do website development, public HTML is normally set for default access. And you have to change it to 777 or 750 or something to make it public, give it access. So same types or sets of permissions so far, the read, write, and execute, also work at the directory level. They also work, by the way, on devices. If everything's a file, and you have file permissions on everything, then everything is changeable, which is pretty universal. So you can exclude devices, you can exclude directories, you can exclude files from anybody you want. You can create groups and put everybody in the group, give them all access to a drive, all access to something. Common utilities for managing files and directories. Well, we saw PWD's password, our current directory. Print out the current directory. We saw cat, ed is an editor, vi, emacs. I showed you nano. I like nano is better. ls, rm, mv, cp, ln, make disk, remove disk, lp for print a file. Not going to really print a file unless you have a file printer. So this is kind of the basic file manipulation stuff. So some people at this point might be wondering, what in the world are these commands I need to know? Or, why in the world she keeps showing me these commands? I don't know what this is what's going to be on your final exam. So on your final exam, you'll have some multiple choice questions that are asking you about the RM. RM is used to remove directories and files and something else. True or false? False. Can't remove a directory with RM unless you go -R to remove recursively, but you can't use RM on a directory. You have to go RM dir directory. So that's what the test's all about. RM removes a file. Can you make remove a file, remove a file, copy a file? What does ln mean? It's a symbolic link. To link to something. A lot of the commands are user-friendly. What you're going to be tested on are the commands that are in the lectures, the ones I'm giving you, the ones that are in assignments. If it's in an assignment, if it's in a lecture, if I talked about it, you're going to find it on the exam. Most of them are going to be multiple choice questions, and there will be some fill in the blank short answer questions. Well, you'll write a command. Now, the syntax for the command is not an all or nothing. If you leave out a dot or a forward slash, that might be a problem. But if I told you to give me the absolute directory and you give me the relative, that's a wrong answer. If I told you to give me the absolute directory but you got it off by 1 or something, that's okay. It's close enough. So you don't have to, it's like programming, you don't have to be exact. I'm not going to take off points for syntax error. You misspell remove or something, I don't know. You misspell something. As long as you're in the same ballpark for what it's supposed to be, that's how the right or wrong works. And the way that the exam's set up, I've actually already started working on it. It's fairly straightforward. It's no way you're going to, if you know it, you know it. You don't know it, you don't know it, is how this works. So there's no way you're going to, oh, but I meant to say RMDIR, but you wrote RM. So I don't know, I don't know how you could not have thought that's not even close, Anyway, long story short, you don't have to memorize all of the change octal. You don't have to memorize numbers. I'm not going to ask you, what does it mean to give it 777? Well, you might already be able to answer that question. It's full everything. Read, write, and execute to everybody. And how do you get that? You add all the numbers up and go 7 is the highest number. All the different combinations. Well, that's pretty no-brainer. Okay. But there's some questions where it'll be like, change mod plus R file. What does that do? Or something, Or a TR space, and then you've got uppercase S, and you got something else in there, and a bunch of stuff. And what does that do? Translate. If you don't know what TR stands for translate, you're not going to know what the question means. So translate's in the next assignment you have, actually. grep, cat. I'm not going to ask you questions about VI. I wouldn't be able to answer those questions. What command in VI closes it? I know that one. Q, exclamation point, or exclamation point Q or something. I don't know. Not like that. It's basic stuff. In terms of Unix processes, let's go back to the lecture here. Definitions, we got the program, it's a collection of bytes. We got the image, it's the computer execution environment. You got the process, it's the execution of the image. And we got the multitasking. Many processes can execute simultaneously in Unix. Unless you got 2 processors or 2 CPUs. I don't know if you're really getting true simultaneous anything on any operating system. But user process groups. So we get the process ID that's associated with every running process. It's assigned upon creation. We got the group ID. So we got a bunch of IDs that go along with the process. Because if we're going to give access to groups to processes, we have to put a number on it so the kernel can keep track of it. So which processes belong to? There's the user group, there's the user, or there's the entire system like the kernel. So kernel's got process IDs that are associated with groups of processes that are owned by the kernel. You have one when you log into the system, so does any group that you belong to. Foreground processes and background processes. So we use an ampersand, and we're like, what in the world does that mean? You're just putting it into a different process group. The ampersand puts it into a different process group. Is it all run on the same processor? Yeah. Is it all doing the same thing? Yeah. So we notice the ampersand symbol. Probably going to be in the slide next. Foreground is foreground. You run it, it's automatically in the foreground. You don't have to tell it to go in the foreground. If you want to put it in the background, you create it, and it's not in the foreground, it's in the background. Well, I like this slide. Processes created by you, not in the foreground. It's not in the foreground, it's in the background. So how many you got? You got 2, foreground or background. Well, you get a shell, can open up another shell, that can open up another shell, that can open up another shell, that can open up another shell. And you can have a foreground and a background in each one of those shells. But all of those processes are created by you, so technically they're all in the same groups, just in different environments. The shell is giving you the environment. Which is kind of interesting because you think about it and go, what's a shell? That's an interesting concept. So in the undergraduate computer science, the operating systems classes, usually the first, I think if somebody was in my operating systems class, they would be running a shell as their first assignment. because the shell is core to the concept of what the user mode actually is. So the init spawns off the shell. You log in, your login script runs a shell for you. It's defined in your login script. That's your graphical user interface. You're like, nah, that's a poor man's graphical user interface, if I've ever seen one. There's no GUI to that at all. But that's your command interface. It's all ranked under that shell process. So everything inside of that shell is in the same group. So imagine a big old tree of hierarchies of processes running, and you're just one entry into it somewhere. You're just spawning off more processes from that point. So process relationships. A process spawns other processes. Everything you type inside of shell is running as a sub-process or a child process of the shell. So you can do it yourself within your processes by running fork, which is a system call. And creating processes is the parent process. So you're the parent, you're the shell, and you run ls, that's a child process. So newly created processes are children. Fork returns 0 to the child process, and fork returns a process ID to the parent process. Why do we care about that? Well, because we care about the child processes more than the parents. Because the child processes are what's running. And then when the child process dies, or goes away, terminates, because it's going to end eventually, it signals the termination back to the parent. So if the parent doesn't know about the child, there's a problem, especially if the child, they can't check on the child, they can't do anything with it. So the parent always gets the child ID that comes back to it. So, but the child never gets the parent, which is kind of the most ironic thing. So it works in one direction. So execc, and the two here, there's just two common variations of, don't worry about it, is to run. So execc is a system call that you generally execute inside of a. Now, if you were going to call anything a lightweight process, I'd call execc a lightweight process. Because execc creates a thread to execute something, and then the thread never actually makes it to full childhood. The thread gets created, runs the program, and then it quickly terminates and cleans up itself. So it's kind of like half a thread. So it's kind of not a thread, it's an execc. So execc is the system call that you use constantly. Every time you type ls, cat, change mod, everything you run is an execc system call. You just never have to write it. Other programming languages, they call it system. Put system in there with ls or something for C programming to run a system call. Well, system call goes down and runs execc. So why don't you just write execc in there? Because execc comes from the thread libraries, system comes from the base libraries. So it's just two different libraries. So. And system is not a system call. System is a API call, high-level API call that runs the exe system call. Execc is the system call. Overwrites itself with the code, initializes the data of the new program, and thus eliminating the execution of the new program. Starting the execution of the new program. So wait puts it on hold, so the parent can suspend its execution until one or more of its children have completed. So it waits the system call. Upon termination, the process can set an exit status available to the parent. Exited normally, exited abnormally, which means I was successful or not successful, which is helpful for the parent to know, because the parent's going to need to know what to do after that. So here's an example. There's a program that creates a new process to copy files. Kind of interesting what we're looking at here, assuming that we have the fork. We have the fork, and check this come back true if it's equal to 0. If it is, then we're good. If it's not, if it's negative, then we're bad. We didn't get a fork. We didn't get a process. If we got a process, we're in the child process. Because forking a child, this is the one thing you can't teach undergraduate students to figure out. They can't tell. Well, half the time they don't know that a process that their running C program is the first process. And then when you fork a child, you're in the child. Because fork creates the child, and only one thread is running at a time. So if it's not the parent, what's it going to be? And people always go, at this point, when you see this child process after the fork, they go, how do you go to the child? It's like your process space is already in the child. The child is already active. And then they spend a good couple weeks trying to figure out, oh, wait a minute, what about the parent? So then I see the assignments when they turn into shells, and it's their program that creates another process that creates another process. And then you see some EXECs in the third process. Thinking, how many processes deep do you got to go to get to an EXEC when they don't get it? That they're the parent, and they're creating a child, and once they create the child, the child's going to run. So you could technically create a shell that went like 12 deep. Yeah, it's going to be the same processing, same work is going to get done as if you went 1 deep. So generally you can tell if people are understanding the concept by how many processes are they going to create before they actually get to the XCC to run a shell, which is actually kind of funny. Anyway, this one here is the child process. It's going to run EXCC, and then you're looking at L. All those L's, F's, M's, so many different variations of that command. Depends on the thread library that you're using, and it depends on what parameters you're going to give it in terms of what you're going to write. Then we got to wait on the parent process. See, this is inside the if, and then outside of the if, we're going to do wait. The funny thing is, sometimes, depending upon the system you're working on, you don't even have to put a wait in there. It's automatically waiting. You don't have to actually wait anything. But it's nice to put a wait in there. Put a wait. And then print copy. Yeah, we're done. This is the printf, the copy done, isn't going to happen until the child sends a signal back to the parent that, because this if is going to keep going, this EXEC is going to return eventually. When it returns, it tells the parent, which is us, we're the running program, that we're done. And then we're going to end up having to, come back to the parent process, and then by that time the wait's over with, and the printf happens. So that's why I say the wait. If we're in the process, if we're in the child, the parent is waiting anyway. So, but you could put a timer on there and return 0 on a wait. If you did that, that would solve the problem going back to those undergraduate students who put a process inside of a process inside of a process inside of a process, and then they run EXEC. And then the EXEC ends, and it only tells the outer process, hello, you got to go all the way back 5 steps to the main process to continue because you're stuck. And generally the program hangs or something. I can only run 1 command. And after I run that 1 command, the whole thing stops running. Like, yeah, because you're like stuck 5 processes deep, and only one of them returned. You got to return the rest of them back up. This EXEC has an auto return. Otherwise, the child's not going to return. You actually have to make the child return. So, anyway, enough picking on poor undergraduate students. But that's generally what you see when you ask someone to do a shell. And I believe it or not, I saw this in the operating systems class here. The shells, 20 processes in practically. No, I'm kidding. It's usually about 2 levels. They don't realize that you are the main. All you have to do is fork one. All you have to do is use fork 1 time to get the child process to run anything you want in the shell, which is interesting. Anyway, fork operations. Here's our fork operations after the fork. The shared text is shared by the parent process data and the child process data, so in the shared text area. And then after EXEC of the program 2 in the child, inside of the child, after the EXEC, parent process data and child process data. Further down, you've got the program text data that's unchanged from the parent, because parent's paused at this point. And then the child's program text is the one that changes. So, and then when that child ends, that gets cleaned up, goes back to the parent. And we start over again, we run another process. So here's our Unix process genealogy I was trying to tell you about. Here's the family tree of the processes. Init is process number 1. I thought I remembered. Fork init's the processes. So forks init process, excuse me. Init process 1 forks the init process. We got init for tons of different interfaces. So we have init for shell 1, 2, 3, 4. Then we have other things you can underneath it. Then finally we have, or getty, if we're going to run 3. This is just an example of running a sequence of 3 sessions. And then we have the login exe, and then we have the bash shell that's run. Once you hit the bash shell, you're set. So when you're coming in here. to log in. So you're going to go and SSH to the server. You're coming in the login executables. Once you go through this level of processing, you get one of these. But you might have 60 of them or so, depending on how many accounts are on here. So it's going to take you down to the shell level. So in terms of process permissions, we have the real ID and one or more real group ID sets at login. So your login script is going to set your process permissions. So processes. Anything you create is owned by you. Somebody has to set your login. It's usually done through your login script. When you log into the system, your process, your IDs are set for you, which gives you the ability to run certain commands and to have access to certain features and directories and stuff. So the effective user ID and the effective group ID determine the process access to read, write, execute files and directories, etc. and so forth. UMask is the file mode creation mask used to show you that. Created by the process, it will show you the IDs. So the same system you use for files and directories, very similar to the concept of the process. You belong to a process group, so, which is interesting because user account processes don't have root access, so you can see everything in the other student accounts, but you can't open it, can't read it, which is interesting because usually well, I did get this from the online. I'm also teaching an online version of this class, and some of the online students say, hey, did you know we have access to everybody's information? A couple of people actually sent me email messages like they're trying to do me a favor. I'm like, yeah, try to do something. Like one guy was actually arguing with me for a while. He's like, oh no, it's totally not safe. Everybody has access to everything. Everyone can see everything. Everyone can touch everything. It's total cheating going on. I'm like, really? Try changing something. Oh, maybe I can't do anything. Like, yeah. Like, you might think that you could cheat, but you can't even you might even be able to change directory in there, but you're not going to be able to do very much because it's locked down in 5 different ways, actually. Your user account is locked down by your user login process. You log in, you're a process, by the way. Your process is located by your student. At the higher level, if your process doesn't have access to all the other processes, you're on an island of your own, whether you can see something or not. And does it really matter if you see what other people are doing? If I were the student, I'd go, hey, you know what? I'm the only one who hasn't done anything yet. But the thing is, the assignments are all about making the directories and making the files. So if I saw that there's what were the things we were doing? I don't even know what they were. Banana, pizza, and apple or whatever in somebody's directory. Breakfast, lunch, and dinner. If I saw breakfast, lunch, and dinner in somebody's directory, I'd be like, oh, maybe I should do breakfast, lunch, and dinner. You're still going to make breakfast, lunch, and dinner. It's not going to make itself. You can't even copy it. You can't even take that one and copy it. You can't even touch it. You can see it. That's about it. But you can't touch it. And the reason why you can see is because then at least I can log in, and at that level I see everybody's stuff. But I have read, write, execute, so I can actually change it, I can execute it, do whatever I want to it. That's because my login is coming in as a different user group. So it's a different branch, so I have different permissions. So, long story short, I found it humorous. Those people are not in this class, so I'm not laughing at anyone in this class, but I thought it was humorous, the adamant, very adamant. It's like an entirely bad thing that they were going to plagiarize and all these things were going to happen. I'm thinking, you know what? Why don't you explore Unix a little bit more? Why don't you go in and test it out? See if you can do it. So anyways, a learning experience. You realize, oh, that's different. If you were on a Windows system and you saw that, first thing you'd be going, oh my God, everyone can just copy everything. Yeah, because you can. But not on Unix. Unix is totally different. It's all by the user. It's all by the process. In this case, it's the processes that were set. You log in as a student XYZ. You have process permissions for XYZ. Not only that, but you have the directory and the file level as well. So, but it's all set by your root login. Signals. We have signals. We have semaphores. Well, signals are semaphores used for inter-process communication. Signals used all over the place. Messages. So a message a process can send to a process or a process group if it has the appropriate permissions. So you can send signals among your processes. What does this mean? Can't do this in Windows. Half the people don't understand this from systems programming either. But you can send, it's a signal.h library. You can send signals, message passing back and forth between processes. One process can tell another process something. Send information back and forth. What does that do? It helps with inter-process communication. It also helps with sometimes of dividing work out. This process can do a backup. And when process is over, it sends a signal to another process. Okay, I'm done with my backup. Can you do something else? And then the next set of processes maybe does a archives it, tars everything. Because a lot of people like to tar backup or to do kind of, overnight backup utilities and stuff like that. Or maybe they could check to see if anything has changed. You have one process that checks to see what's changed, gets a whole list of what's changed, and it signals to the other process that might be running already to do something else. These processes are not starting and stopping in a sequential fashion. They're all running simultaneously. So the other process goes, okay, this directory is ready. Okay, that one's ready. This one's ready. It's handing work off and exchanging, and they're all working on pretty much the same task simultaneously, and they send signals back and forth to tell each other what to do. Best of both worlds. Got all the communication that goes on. Supported by system call interface. Can't do this in Windows. Message number represented by a symbolic name. We come up with names for it for each signal. The receiving process can explicitly ignore the signal. You can tell someone to do something, but they don't necessarily have to accept it. Specify the action to be taken upon a receipt. Let's just say upon, not a prawn. Receipt, signal handler might actually work. Otherwise, default action takes place. Usually nothing. Actually, nothing happens if you don't answer the signal. So here's an example. And when a child exits, it sends a sig handle signal to the parent that says, hey, I'm done. And then the parent picks it up and says, okay, automatically, all right, you're done. I'm going to clean up your mess. And I'm just going to finish processing myself. And then the parent might issue a wait to tell the system it wants to catch the child signal. So that's what we did in that. That's what was in that example, was the wait. And when the parent does not issue a wait, it ignores the sig hold signal. So the signal comes back. Depending upon your system that you're on, if you don't put the wait in there, you don't get the terminating signal that comes back out of the child. Otherwise, how's the parent gonna know when the child's done processing? So we have a signal that goes back and forth. And the signal is going to be in a table, and we have a process ID, we have a process owner, and we have a signal that goes over there. So it's just like a message mailbox exchange. Actually, it comes in. I shouldn't say it's not a mailbox; it's a direct communication mechanism. So when you learn about inter-process communication, generally you learn about message passing, semaphores, mutexes, and indirect and direct communication. And, pipes are an inter-process communication too. Actually, that's what we're going to get to next. So, signals, read and write regular files. Pipes, kind of like the intent, actually, from the Android I was talking about earlier. Sends information back and forth. So, the process B tries to read from a pipe. So, returns data if process A has written to the pipe. All right. Returns end of file if no other process has pipe open for writing, nothing in there, or suspends until the execution until process A writes data to it. You define process A, define process B, you create the pipe between them. And then A waits for B. If A's over here, A is going to send something, and B, not necessarily synchronous, it's asynchronous. A can write whenever it wants to write. You open the pipe, you establish the pipe by using a command. We're going to see the command. Actually, you're going to write the command in assignment number 5, actually. Pipe is an upside down, it's a straight up and down line. It's on your keyboard. On my keyboard, it's underneath my delete key, above my return key. It's a shift. People go, what is that key used for? It's a pipe. So, what we saw earlier, we could pipe the output from one program. You pipe it to the input of another program. That would be process A and process B. So if you're going to do that, then B waits for A. If B tries to pull from the pipe and the pipe's empty, it gets a message that says, hey, end of file. So then it can try again later, or it could just suspend. So it's inter-process communication. It's the way process A and process B can communicate instead of signals. So it's just like signals, the same effect. But signals are files, messages that are passed back and forth. A pipe is actually kind of a connection. It's in a kind of an interesting way. So unrelated processes. That's a typo. The E and the L are switched around. Unrelated processes. First in, first out named pipes. So so take this with a grain of salt, because some Unix systems support named, anonymous, generic, and then you got all this terminology for a pipe. A pipe is a pipe is a pipe. It's a connection from point A to point B. Actually, if you want to think about it like a metal pipe or a hose. Put a hose up there and you toss the data through the hose. It's a pipe. So that's why I couldn't understand why in the world are they going to use intent for that. Word doesn't make sense. I just call it a pipe. So anyway, System V, IPC, we had message queues, semaphores, and shared memory. Usually we get sockets for client-server model. TCP works with sockets, datagram packets work with sockets. We're going to talk about sockets tomorrow. Socket and a pipe are pretty much the same thing. What does a socket do? It's a pipe you attach to an open port. So instead of sending one process A to one process B on the same computer, you use the socket to send from computer A to computer B, port to port. So on computer A, you create a socket, you bind it to a port, an IP address. Computer B, create a socket, bind it to a port on an IP address. And then you use TCP or UDP, and you send a packet from point A to point B via the socket. You read it and you write it to the socket. It's the same thing as a pipe, but it's a pipe between two computers instead of a pipe between two processes. So try to have an undergraduate student to write a UDP and a TCP program, and then they realize, oh, it's all over IP. IP is pretty basic. The IP doesn't do anything. If you remember, IP stands for Internet Protocol. Yeah. What does that tell you? Same thing as a lightweight, whatever. Internet Protocol. Oh, nothing. It's a naming convention / addressing scheme / underlining middleware that connects sockets together. And then the TCP will transport communication protocol, and UDP, unreliable data transport protocol. What does that mean? It's just moving the packet. So you use the IP to connect the sockets, and then you use the transport layer right above it to send the packets back and forth. Are you going to send it unreliably, or are you going to send it with a bunch of overhead? This world has gone overhead. Everything's TCP based, because everything is, you send point A over the socket, you say, hey, I'm going to send you a file. Okay. Wait for your okay to come back. Okay. So you send the file. Did you get the file? Okay, I got the file. It's like 3 messages got to pass back and forth just to send 1 gram. 1 datagram passed from point A to point B. Lots of traffic. But it's reliable. Problem is, we started out UDP. We just toss the packet through the pipe. So you might think that, and this is true, pipes and signals are unreliable. No overhead. Easy. Sockets can be both. Sockets can be reliable or unreliable, depending upon what transport protocol you're going to use. And we put the responsibility on the transport protocol to say, we want all this confirmation and acknowledgement of everything that's going on, or we just want to throw it out there in the street. So it's like the difference between the guy who takes the basketball from one side of the street and just throws it, hoping it's going to make it, but he never really knows if it makes it to the other side of the street. Or the same guy who dribbles the ball constantly from one side to the other side, and he gets there and he's with the ball too. So if you're going to do that, you might as well just throw yourself through the socket. So, which is pretty much what you're doing. Process environments include process ID, process groups, open files, working, all this inventory, all this stuff is being kept for each one of these processes in the communication environment. Really effective user IDs, file creation masks, resource limitations, signal action settings, set of named local variables, everything you can possibly think of. The file descriptor. I always like this concept in C, systems programming class. When you have to write a C program that does a low-level F open, and then people who don't like pointers go, why do we have to make a pointer out of that? Oy vey. It's because you're going to go open up a file, read all the contents of a file, and stick it up into a memory address. What do you get returned from that kind of system call? A pointer. So they call it a file descriptor or file number, because we do buffered I/O now. We don't do rewrite to that disk. It's too long and complicated. So each process associates a number or a handle called a file descriptor FD with each file that has been opened up. Basic Unix kind of thing has transposed into other languages as well. It's become pretty much the de facto standard for how you're going to open and close files. It's generally an fopen kind of command, or it can also be, some interpreted in other APIs as different. So login3 files are associated with terminal. Remember I told you everything on the computer is a file. So standard input, standard output, standard error. So it's file descriptors 0, 1, and 2. So if you rate your own file, it's going to be 3 or above if you open up your own file. So if you have that, then you have stdin, stdout, stderr, whatever, error. I think it's err. And then you can write to it. Just like you can cout something to, cout actually writes to the file output descriptor. So you can write your own cout command, actually. It's really easy. This is C++, this is Unix. By cat, my file name, directional operator. No, I'm not going to do it. And then you write stdout, out, and it'll write to your screen. That's what cout's doing, actually, or printf actually too. Well, printf is formatted. Printf will actually parse those commands in there, translate it, do some other stuff to it, then put it out. Cout's more primitive than that, actually. It just runs which is actually kind of funny, because when you write the command, you're using the directional operators. I'm thinking, why in the world did they even bother with that? Just put cout space in the name of whatever it is you're seeing out, because essentially that's what it's doing. It's using the directional operator to output it, to redirect the output to standard output, which is file descriptor 1. You can actually replace standard in, standard out, standard error with 0, 1, 2, and it works. So I think it's going to be in this lecture, but it may not be, but we'll see. Process inherits the parent's file descriptors. So all the parent and the child own the same files. Nope, not in here. It's probably going to be in another lecture. You can actually, it's probably going to be in one of your assignments to write to standard output. You can use 0, 1. You can just go, ls with a arrow facing to the right, 1 or 2 or whatever. Write it to whatever you're not write it to 0, because that's the input, I think, if I remember this right. Input is 0, so you're going to write it to 1 or write it to 2. So ls arrow 1. It's the same thing as writing ls, really. Why you're gonna do it? It's the same thing as writing ls with the arrow my file, and it puts it into my file. I can also put it into 1 too. Why do you want to do that? Because maybe you're writing a background process, and maybe you want the error report to show at the end. So what you're going to do is at the end of the script that runs for 2.5 days, then it's going to print to the standard output. Something is going to be finished, successful, not finished, or something. Probably not going to be a lot of output, or maybe put it into standard error. Then you can go in and cat standard error. It's a file. And see what kind of errors came out of that. So if it's not going to the output, if it's going to error. If you're catching to send and redirect to standard error, then you can see what's in that file. And the files are shared among all the processes. So not one process has control over the input or the output or the error. All of them do. They all work the same. So they're shared files. So they have signals. Actually, they work with signals, they work with pipes, they work with everything. Process subsystem utilities. So we know PS shows you the processes. Jobs is not on here. It's not actually supported in Unix. It is a Unix Linux kind of thing. It is on some systems. Kill a process. Wait, no hup. Makes a command immune to the hang up or the termination signal. Let's not terminate it. Sleep, nice. Run the process at a low priority. I'm going to be nice. Everybody else can go before me. You just put nice instead of just running ls. You go, nice ls. Yeah, it doesn't really matter. ls is going to run. Run it nicely. Right, there's no nicely, it's nice. Set user ID, set group ID mechanisms. Just the same way as change mod, really. So the mechanism is patterned. It's supposed to say pattern, not patented, but patterned. So it's a pattern that you're typing in, very similar to change mod. Process effective user IDs are different from real IDs when it executes a set, or set real ID, or a set group ID. Example there is changing your password changes. So the process is effective on a user ID or group ID becomes that of the executable. So basically makes the command work or not work depending upon who you are. So security problems. Permissions on executable programs. Yeah, and directories in which it is contained must be correct, otherwise easily replaced by a Trojan horse. Well, here's the thing. You get the same problem with Windows, actually. So I don't know if you guys taken the ethical hacking course or anything like that, but they teach you a bunch of stuff in there about replacing system files with fake system files, as long as you have permissions to do it. And most computer systems, well, most Windows systems have permissions for everything. So unless you put up a firewall or something like that. So you go in there and you change something in the system 32 folder or something, and you put something else in there. And then all of a sudden you have something weird. Well, imagine how easy it is to do this with Unix. If everything is accessible via user IDs and process IDs and everything, you don't even have to log in. You just change the ownership. Somehow figure out how to get into the account. Change the ownership yours, log in as yours. Do everything you want. Change stuff around. If you make it all 777, it's open to the world anyway. So it's pretty much easy to replace system files with other files. No problem. It's the same problem. Some systems remove the set user ID and the set group ID bits whenever files are modified as a security precaution. Because if you're going to set the user IDs, you don't even have to have access. You're supposed to have access to the user who owns the ID to set and change the IDs. But if you leave it so the permissions are kind of skeptical, and you can log in as something else as a member of the same group, then you can change the IDs. Change the IDs, you change the belongings. So, our next topic of discussion are shells. So, an overview of the shell. So, you're going to get this in one of the assignments, I think. Actually, one of the first assignments, yeah. So command line interpreter, we've actually kind of seen this stuff already, and you did some comparison already. So a command line interpreter and programming language between the operating system and the user. Most people argue with me and say, kernel's not a shell. It certainly is. It's a command line interpreter. You type commands, the operating system runs it, kernel interprets it. You have a kernel module. Actually, Perl's a base programming system, along with C, actually. You can get a C shell. Load up the C shell, or just right here, C shell, and write printf, and scanf, and all your C commands, and it just runs in the shell, no compilation, nothing. So, just like Perl. And we got shell scripts, so that's going to be the theme of our next lecture. The files of a Unix and a shell commands executed by a Unix shell. So you actually made a shell script on day number 1 in here. Where there's different languages to make one too. What we're going to do is just take it a little bit step further, make it a little bit more elaborate shell script. I don't believe you have to do it in any of the assignments, but because we already did it the first or second one. But, most Unix admins, they write shell scripts a lot, because how else are you going to automate stuff? People don't like running commands constantly. If you can tell it into a server, start a script, then you can go to the beach. And then they're going to say, did you back up everything? Yeah. Did you clean out that resource folder? Yeah. Did you tar everything and do all that? Yeah, no problem. Did you search for this? Did you find it? All these other things. Oh yeah, sure, no problem. You can even actually nowadays you can even have shell scripts that, well, when it's done, send you an email message. Hey, I'm done working for you. Oh, okay, thank you. So if you're a smart user admin, Unix admin, you can actually have scripts that will go through and check which users haven't logged on yet, or which users are still logged on, or better yet, if a user's still logged on, log them off. And these are kind of like background programs that run. Common stuff actually comes with timeout this, timeout that. Some of it's handled by system configuration changes that you can make, but for the most part, admins do a lot of cleanup work, backing up stuff, testing for connections, doing a bunch of troubleshooting stuff. You can just run a script that tells you if there's any problems, and then have the results emailed to you, or better yet, just leave yourself a little text file, log file. You can just log into the log and look at the log file. Wow, Colorado seems to have a problem. Maybe I should log into that server and take a look to see what's going on. We're almost running out of disk space over there. I wonder why. They can figure out stuff. Oh, let's just clean out all these temp files. You can pretty much figure out how have the computer do your work for you. Actually, that was kind of the funny thing. So I was listening to this guy who was talking about social media. Actually, it says in the beginning of computing, a little tangent here, but you might find this interesting. In the beginning of computing, the computer helped the user, and the computer saved the user time and energy so that the user could get more work done. Oh, you heard this? Now it's the exact opposite. I don't remember how the expression goes. There was a news talk guy who said, and I listened, he's going, man, he's right. Now we work for the computer. If we don't log on and check our Facebook, our profile is going to be out of date. And he went through 5 different things about social media. If we don't check our email, our account's going to overflow. And we're going to have these urgent messages that we just won't have the information for that we need. And we won't be able to schedule our day unless we're checking it constantly, every 5 minutes. And the more we check it, the more work it gives us to do. Anyway, it was kind of a weird scenario that's flipped. We're now working for computers. But I'm not doing it. I refuse to work for the computer. I refuse to participate in that. So now the computer, I'd like to think that the computer's still working for me. And I'm not working for the computer. But I have a lot of friends who are working for their computers. Seriously. They have to take a picture of everything they eat. And then they have to put it up on the Facebook or Twitter or Instagram or something like that. And they constantly, oh my God, I've missed 10 messages. So they're standing there in the middle of an important meeting reading this stuff and replying back. So I don't work for your computer, which is totally wrong. Anyway, but yeah. Anyway, the guy, I didn't deliver it the same way. If you catch it, it's on radio. It's on a news talk radio show, a local station. And they probably have done many skits. He sets it up and then he delivers it differently. It's more of a punchline to it. But it's kind of ironic when you think about it. But Unix is supposed to be working for you. You're not working for Unix. So you write a bunch of scripts, you get it all done, so you can go to the beach, or you can go to the Super Bowl or something, and you don't have to actually be on the computer. That's how life's supposed to work. So anyway, it's interesting what luggage people carry around just to support their computer habits, computer life. All right, working with shells. Shell invoked automatically during a login session. So you get a shell, and then we've been loading shells on top of that. Reads a specific startup file for the initialization. Display prompt, waits for the user commands, executes user commands. We've all used a shell, so we all know what we're doing with the shell, I hope, by this time. So here's the redirection of the input and the output I was talking about. We saw this actually already. So if you type in, I think we might actually see the standard output in here too. A redirection of the output symbol. The double arrows actually work in here. So we have the single arrow or the double arrow with the man ls for, let's say, info.ls. We'll print it out to ls. We have the arrow going this way, the opposite direction for input. cat. So input input.data. So send it to cat, or using filters or pipes. So cat file 1 pipe word count -1 counts the number of lines in a file. So the double arrow. It's probably in another section here. I know I have another example with output and the double arrow in here too. So shell core features. So here's what, in the beginning of time, instead of learning how to click and drag and drop like modern day users did, back in the start of computing, Unix people learned how to memorize commands, or wrote down commands and had a list of all these commands they had to do. So simple and complex commands. All the shells had different commands. So it's like everyone invented their own shell. The Bourne shell, the Bash shell, the this shell. They all had separate commands. And then it was just like Windows and Apple, or Microsoft and Apple. They slowly became one. Both systems pretty much are giving you the same thing. All shells are pretty much supporting all the same features. A couple of them, actually, the one I didn't like was a couple, I don't know, around the late 90s, they started supporting DOS commands. Because DOS people started using shells. So dir started working, directory dir instead of ls. Which is like a little ironic thing. It's like, and then this shell supported it. Okay, so this one's going to support it now too. This one supports it, that's so forth. So we had one originally for C, we had one for Perl. Well, Perl's still Perl, but we had Bourne, Bash, I don't know, just put out a dozen shells. They all were unique because they all had their own set of commands and they all did something a little bit differently. Now they're all the same. You can't really tell the difference between them. They're not the same, they're still different, but they're all the same. It's kind of like, what can you do on a Windows box that you can't do on a MacBook and vice versa? Same. If you're just using the windowing system, you can check email on both systems. You can write Word files on both systems. You can do everything on both systems. You can do a little bit more on the Mac. But the basic everyday operation as an appliance, they both do the same thing. So why do you need two of them? You don't, but you know how many people own two? A lot of people own both. Anyway, long story short, it's a shell. Desktop operating systems are pretty much doing the same thing. They support pipes, wildcards, command substitution, background processes, shell variables, here documents. So here documents are pretty interesting. You could put together a substitution system. Okay, so we used to call this mail merge in the past. We don't do mail merge anymore, do we? Because we don't write envelopes. We don't print out envelopes anymore. Instead, we send email messages. So you can still do it with email, where you write a document and you put substitution in there, and you run it through a list of names. You substitute the names and everything, and then you use Pine and you just send it out. Mass mail, called spam, but it's personalized spam because you can put stuff in there. You know, hello, Barbara. Welcome back to fill in the blank. And you just substitute for everybody. Simple commands supported. So simple command is a sequence of non-blank arguments separated by blanks or tabs. All right, first argument is numbered 0. We saw this actually with echo. So you've seen this working already. So there's a little bit of review. They're called simple commands. So, they're simple. First argument is 0. First argument, numbered 0, specifies the name of the command, and then we have the substitution arguments. We could take those and we can put them into what's called environment variables if we wanted to, and use echo to print them out, which we did, actually. So they're passed as arguments to the command, and arguments are file names, path names, directories, etc., and so forth. And then we have more complex commands. So complex commands, command groupings, and conditional commands with wildcards. So if you're going to write an effective script, you're going to use wildcards. Take everything from this directory with an asterisk or with a question mark and say, well, match a single character or an underscore. Match 1, 2, 3 characters or 4 characters. I think we saw this with find, actually. If we haven't, you're going to send assignment number 5. So list matches the character in a list. Upper to upper, or excuse me, upper, lower, lower, upper. Matches characters and ranges of lower, upper inclusively. And then shell scripts. So you write the shell script. We've seen this already in assignment number 1. And then you change them all to make it executable. What do you have? Executable file. Process. So it's just like an exe file you create in C. You just don't have to learn a programming language. So If you want, you can actually use the C shell and run regular C without compiling it. So when the script is run, kernel determines the shell that's going to be used by the pound sign in the beginning. A lot of people will put the pound sign in there because they'll use a command that they know works in a particular shell. And if they tell the kernel, use this shell, then it's better and more reliable. It just picks whatever shell it's in. Command might not work. Something might happen. So you specify the hash sign. So when it's interpreted by the C shell, it knows it's a she. It's going to have C printf and scanf and things like that in there. Is that the student or is that the? Oh. Is that? I thought maybe that was the door check. They're not checking it as often.
Yeah.
I noticed it. It got a little excessive last weekend or the weekend before. It's not bad. So path name is used to interpret the script. And if neither Rule 1 or Rule 2 applies, the script is interpreted to be a bourne shell. Now it's the bash, or excuse me, it's bourne, which is the more default one. I keep thinking bash because that's what the Mac uses, but you can actually change your shell. It doesn't have to be bash. So here are documents. So we got the shell that provides alternative ways of supplying standard input to commands. So the shell allows our inline input redirection using the double arrows, called here document. So here's command argument with the double arrows with arbitrary delimiters or whatever it's going to use, like a comma or something like that. Now there's somebody talking in the doorway. Shell variables. So one of the beautiful things about a shell is the environment, and which is why most people would use multiple shells, or some people use multiple shells, I would say most. Because you can have some shells that have different environments in it. So you have a split personality, you want to say that your name is two different things. You can set a name in one shell and another name in another shell. And then when you pick the name, in whatever command you're going to use or whatever document you're going to use, whatever, it uses a different environment setting. So environment variables to shell scripts are like variables to C programmers. Integer I, float F, all those variables. You can do that with shell scripts, but you're not writing it like declaring it, you're just doing it whenever you want to do it. So I say, my name, Barbara, and I define my name as Barbara, and I make a shell variable about this. So shell variables, several mechanisms for creating variables. So the variable is the name. It's presented by a string value, like my name or something, or name. We have one, it's called home. You know, $home tells us our home directory. User, who am I, comes back and gives us our user shell environment variable. It says our user login name. So shell variables can save time and reduce typing errors. And they work as variables. You substitute them into scripts. And then if everybody has one and you set it for everybody and change the login so it automatically sets these variables for you, then you could just say clock in. And then it takes who you are, what time you're at, what system you're in, and it does your clock in or your timestamp or something or whatever. You know, if you're trying to do payroll or something by check in and check out. Better yet, since you turn on your computer, your script can do it for you. Let the computer work for you. Alright, allows you to store and manipulate information. And two types, we have local and we have environmental. So local and environmental, we use it per user or per shell or per everything that the user does in the user environment in any shell. It's going to be the it's not global, so it's the environment. So locals are set by the user of the shell itself. Positional parameter variables are normally set only for that. So here's some examples of some environmental variables. Home, well, we know that. It's the absolute path name of your home directory. Path mail, absolute path name of your mailbox. Okay. User, who I am, the shell, the terminal, type of your terminal, xterm, whatever it is, happens to be your terminal type. Don't know your terminal type, how you can make the settings work properly to give you the type of display you want. So these are set automatically in the environment. We can have positional parameters. We saw this with echo. These are positional parameters just to review the concept. when a shell procedure is invoked, the shell implicitly creates these positional parameters. It's a number, and it has a $sign in front of it. So 0, 1, 2, 3. Which is funny because one of the assignments produced an error when you used echo with something that didn't exist. Yeah, it doesn't exist. And then, okay, so the online class has the same assignments as you guys. Those guys, well, they don't see me, so they don't get all the stuff. So about 5 or 6 people sent me messages. I don't understand. It produces an error. Every time I type in that command, I get an error. And I'm like, and so it asks you for the results. It wants you to write down what happens when you type in that command. And then I get a reply that comes back, but it produces an error. I say, well, go back and forth. It's actually kind of humorous. So wouldn't that be what happens when you type the command? And then I reply again, I don't understand. And then I finally was like, the answer to the question is that it produces an error. Why? Oy vey. Go back and look at the positional parameters. $, there's no such thing as a $0 would work. $sign's an error message, by the way. If you haven't figured that one out yet, if you're still struggling with that one. I have the assignment finished, all except for that one. I can't figure it out. It gets an error every time I run it. The answer is that it produces an error. All right, so we have this one drilled in. We also, the $sign's bad, but the $pound is a number. So not counting 0 gives you the number of positional arguments that comes out of it. And the asterisk lists all of the arguments. So you might want to play around with these, actually. So they're pretty fun to look at, in terms of automating the process. Quoting. All right, so quoting restores the initial meaning to the character that are processed specifically for the shell. So the literal quote are not passed on to this command. So we have the single quote, inhibits a wildcard, replacement variable substitution and command substitution. We have the double quote, or the two marched together, inhibits a wildcard replacement only. So I can substitute, or so restores their literal meaning instead of some of the other information that might be associated with the character or string. Built-in commands. So the shells, this is where I was talking about before. Some of the shells have different built-in commands. They are all about the same. So the commands that are internal to the shell, you can actually write your own and add them to the shell. In fact, you can write your own shell. Take the operating systems, of course you do. You write your own shell. You have internal and external commands. And half the people in that class, they ask, well, what's the difference? Internal is inside of the program called the shell that you're running. And then the external ones are anything you're running. Well, what can I run? Anything. Any command on the entire computer system. Which is the same thing that happens with the shells here. You run anything you want in these things. So the beauty of the shell is what internal commands you have. So on the first day we learned that your SSH, whatever that was that you guys were using, didn't give you bash, gave you something else. Gave you SH or something. And you switch it over to bash, and all of a sudden you got the lovely colors going on there. Well, that's the internal commands of bash shell. You don't get that in the other ones. You don't get color coding in the other ones. So some shells have some trade-offs, some good stuff associated with them. Shell does not have to fork to execute the command. Trade-off, redirection or input, output, not allowed for most of these. It's hard to redirect output from one shell to another shell. It might actually be impossible unless you do a file concept with it. So you're going to take something out of one shell and you're going to stick it into another shell. You're going to write it to a file. So you're going to see out it to or write it to a file, redirect it to a file in one shell, and then open up the file in the other shell. You can't go directly from one shell. You can't redirect the output between the shells. But you can change environment variables, and you have complete unique environments separated from each other, which is the purpose of doing this. So built-in commands, we have built-in commands. They're common in all three shells that we're looking at here. Echo, CD, wait, mask, exec. We've actually used some of these. And so that's the end of this part here. This is a sub-shells. This is going to be a little intense, so it's a good idea to take a break actually at this point. So this is like a 2-part lecture. So let's take a brief break right now. And I think is that the security people or is that the attendance people? Neither. Anybody out there? Or am I just hearing stuff now?
I think they're coming back and forth.
Oh. Let's stop this lecture.